Hello, today me and hello, today me and my friend Mustafa, we will be going across battery technologies in plug-in hybrid electric vehicles. So this is the outline we will be covering. In the introduction, we will be going over what are the plug-in hybrid electric vehicles, its history and development, production and sales of PHEVs, governmental interaction with the plug-in hybrid vehicles, and the types of batteries used. Then we will go through the technology of plug-in hybrid vehicles and its charging systems, operation modes, and electric power storage. Then my friend Mustafa will discuss the analysis of state in terms of costs, environmental impact, and usage. And then we would propose and discuss future recommendations and state our conclusion. So first, what are the battery-powered vehicles? So electric vehicles are currently one of the most developing technologies in the world, since conventional combustion vehicles are producing pollutant emissions such as nitrogen oxides, carbon monoxide, photochemical oxidants, and air toxic that contribute to 1/5 of the total global warming pollution. Vehicles that use batteries as a component for power can be usually sorted into three types, which are hybrid electric vehicles, all electric vehicles, and the plug-in hybrid electric vehicles, which we will be discussing today. The primary distinction between a plug-in hybrid electric vehicle and a hybrid would be that a plug-in hybrid electric vehicle may be charged via a plug rather than through its internal combustion engine. Plug-in hybrid electric vehicles feature bigger batteries than standard hybrids, allowing them to drive longer on electric power and cost less to operate if you conduct a lot of small town trips. Whereas all electric vehicles are powered by a battery only rather than a gasoline tank and feature an electric motor rather than an internal combustion engine. Plug-in hybrid electric vehicles are a hybrid of gasoline and an electric car, including a fuel tank, an internal combustion engine, and a battery, and an electric motor. Plug-in hybrid electric vehicles are powered by both gasoline and electricity. So, history of plug-in hybrid electric vehicles. The first plug-in hybrid electric vehicle was introduced by Renault in 2003, which was the Kangoo Electri Road, where it may be charged to 95% capacity in roughly 4 hours by plugging it into a regular socket. Whereas Toyota stated on January 14 that they will begin selling lithium-ion battery plug-in hybrid electric vehicles in 2010. But due to fast and huge development in this sector, Toyota stated that they will be available to business fleets in 2009. In development, we have supercars integration, where supercars also went into this huge evolution in the automotive industry, where Porsche made one of the fastest hypercars in the modern history, which was considered as a plug-in hybrid electric vehicle, which is Porsche 918 Spider, the total output of 875 horsepower. Also, we have BMW i8, which also contains a 1.5 liter three-cylinder twin-turbo petrol engine supplemented by a synchronous e-drive electric motor, resulting in a total of 369 horsepower. So plug-in hybrids offer the extended range and refilling capability of traditional hybrids, while allowing drivers to use battery electric power for at least a portion of their usual daily driving. In 2009, the average journey to or from work in the United States was 11.8 miles, which is roughly 19 kilometers, whereas the distance commuted to work in England and Wales in 2011 was 9.3 miles. Because designing a plug-in hybrid electric vehicle with a greater all-electric range increases weight and expense, as well as reducing cargo and passenger capacity, there is no ideal all-electric range. The accompanying here we can see in the graph the observed all-electric range in miles for 4 popular US market plug-in hybrids as tested by Popular Mechanics magazine, where we can realize here the Chevrolet Volt has an all-electric range of 48.5 miles. And we also realize here the Ford Fusion, which has 24.5 miles all-electric range, Honda Accord plug-in 15.4 all-electric range, and the Toyota Prius of 12.2 miles all-electric range. In the production and sales, the plug-in hybrids were commercially marketed in 2008 by both specialized and major manufacturers of internal combustion engines. The F3DM, which debuted in China in December 2008, was the globe's first commercial plug-in hybrid vehicle. And then we have the Chevrolet Volt, which debuted in the US in December 2010, was a major automaker's first large-scale plug-in hybrid. Towards the end of 2017, there were around 1.2 million plug-in hybrid electric vehicles on the road worldwide. In 2018, the worldwide number of plug-in hybrids grew to 1.8 million, from a total of around 5.1 million fully electric passenger cars. The US has the world's largest plug-in hybrid automobile market in 2017, with around 360,000 units in hand, followed by China with around 276,000 cars. And Japan also has 100,000 vehicles, and Netherlands around 98,000 vehicles, and the UK with around 88,000 vehicles. As per Jato Dynamics, we can see here in the table, Mitsubishi Outlander plug-in hybrid electric vehicles has been the world's best-selling plug-in vehicle since December 2018. 270,000 cars were sold globally since its beginning, and will continue to be sold throughout December 2021. We have a huge governmental and international interaction with the plug-in hybrid electric vehicles. Several nations have created grants and governmental subsidies for purchasing new plug-in hybrid electric vehicles. Tax, we also see in the world where countries offer tax breaks and exemptions, as well as bonus payments are among the incentives available to buyers of all electric and plug-in hybrid vehicles, and certain alternative fuel vehicles. As of April 2015, 50 of 27 European Union member states offer tax breaks for electric vehicles, including all Western European nations, as well as the Czech Republic and Romania. The Energy Improvement and Extension Act of 2008, which was passed into law on October 3, 2008, provides tax incentives for the purchase of plug-in hybrid electric vehicles. US Obama's New Energy for America plan aims for the deployment of 1 million plug-in hybrid vehicles by 2015, and he pledged $2.4 billion in funding for electric vehicles innovation on March 19, 2009. And here we can notice President Obama trying the plug-in hybrid electric vehicle Chevrolet Volt. We have several batteries used to power plug-in hybrid electric vehicles, and we will discuss the main types. So first, we will sort the different types of batteries used in hybrid and fully electric vehicles, which are lithium-ion batteries, nickel-metal hybrid batteries, lead-acid batteries, and ultracapacitors. We have lithium-ion batteries. Because of its large energy per unit mass compared to other electric energy storage technologies, lithium-ion batteries are presently utilized in most portable consumer devices such as mobile phones and laptops. They also feature a high power to weight ratio, excellent high temperature performance, and minimal self-discharge. Lithium-ion batteries are used in most of today's plug-in hybrid electric vehicles and electric vehicles. However, the precise chemistry varies from that of consumer electronic batteries. There is continuing research and development to lower their relatively very expensive cost and prolong their usable life and solve overheating safety issues. We have nickel-metal batteries. Nickel-metal hybrid batteries, which are often used in computers and medical devices, provide adequate specific energy and specific power. Nickel-metal hybrid batteries also have significantly longer lifetime than lead-acid batteries, and they are also much safer and more resistant to misuse. In hybrid electric vehicles, those batteries have been frequently employed. Nickel-metal hybrid batteries have several problems, including their high cost, significant self-discharge, and heat generation at high temperatures, and the necessity to regulate hydrogen loss. Lead-acid batteries. Lead-acid batteries may be engineered to be high capacity while being affordable, safe, and dependable. Their application is limited by their poor specific energy, low cold temperature performance, and low calendar life and cycle life. Advanced high-power lead-acid batteries are being improved. However, they will be only utilized for auxiliary loads in commercially accessible electric cars. We have ultracapacitors through an electrolyte and electrode. Ultracapacitors store the energy in a polarized liquid. As the surface area of the liquid rises, so does its energy storage capacity. Ultracapacitors can assist cars restore braking energy and give more power when accelerating and hill climbing. Because they assist electrochemical batteries level load powers, they might be helpful as supplementary energy storage devices in electric cars. Now we will go to the technology part of plug-in hybrid electric vehicles. Plug-in hybrid electric vehicles use the same three main hybrid powertrain configurations as conventional hybrids. A series hybrid is propelled solely by electric powers. A parallel hybrid is propelled simultaneously by both its ICE engine and electric motors, and a series parallel hybrid can operate by either mode. A plug-in hybrid car may get a large portion of the energy necessary to recharge its battery from external sources, whereas a standard hybrid vehicle can only fill its battery from its engine. The vehicle's charger adapter might be onboard or external. The process of an onboard charger may be best described as the AC electricity being converted to DC power, which then charges the battery. The capacity of onboard chargers is restricted by their weight and size, as well as the capacity of general purpose AC outlets. Off-board chargers can be as big and powerful as the user wants, but they must be returned to the charger. High-speed chargers can be shared by several cars. The motor windings may function as transformer coils, and the current high-power inverter can work as an AC to DC charger thanks to the inverter on the electric motor. These components are already necessary on the automobile and are built to handle any feasible power capability, so they may be combined to provide a highly powerful onboard charger with little weight and space. This charging technology, known as reductive charging, is used by AC propulsion, and we can observe here the charging cycles of the batteries in plug-in hybrid electric vehicles. So, operation modes. A plug-in hybrid electric vehicle has two modes of operation: charge depleting and charge sustaining. Blended motors refer to the combination of these two modes. These cars can be built to operate an all-electric mode for a longer range, either at moderate speeds or at all speeds. These modes control the vehicle's battery discharge method, and their selection has a direct impact on the battery size and type needed. Charge depleting mode allows a fully charged plug-in hybrid electric vehicle to function solely, almost solely, depending on the vehicle, on electric power until the battery state of charge is decreased to a predefined level, at which point the car's internal combustion engine or fuel cell is engaged. The vehicle's all-electric range is during this time. A battery electric car can only function in this mode, which explains its restricted range. A journey that uses a mix of two modes is referred to a mixed mode. A car may, for example, start a journey in low-speed charge depleting mode before merging onto a motorway and operating into a mixed mode. The driver may leave the motorway and drive until the all-electric range is depleted without using the internal combustion engine. The car can go into a charge sustaining mode until it reaches its destination. A charge depleting journey, on the other hand, would be driven within the all-electric range of a plug-in hybrid vehicle. Electric power storage, depending on whether the goal is to minimize fuel consumption, operating expenses, or emissions, the optimal battery size varies. However, a recent study concluded that the appropriate battery capacity for a plug-in hybrid electric vehicle is determined by the distance the vehicle will be driven between charges. Our findings show that a limited plug-in hybrid electric vehicle with just an AER all-electric range of around 7 miles would be a good choice for reducing consumption of fuel cost and greenhouse gas emissions under urban driving circumstances with the frequent charging every 10 miles or fewer. Plug-in hybrid electric vehicles emit less GHGs and require less frequent charging per 20 to 100 miles. while hybrid electric vehicles are more cost effective. Electric power storage also. In comparison to traditional hybrids, plug-in hybrid electric vehicles usually require longer battery charge discharging cycles, since the number of total cycles has an impact on battery life. This may be less than in a typical hybrid electric vehicle with less totally depleted batteries. Some academics, on the other hand, believe that plug-in hybrid electric vehicles will soon become the norm in the car industry. This design challenges and trade-offs regarding battery life, capacity, heat dissipation, weight, cost, and safety may be addressed. New battery technology is in the works, offering higher energy densities in terms of both mass and volume, as well as longer battery life. Now my friend Mustafa will discuss the analysis of the state.
Hello, my name is Mustafa Shaban, and I will be analyzing the state of some battery technologies, the benefits from using plug-in hybrid electric vehicle or PHEVs, and finally I will talk about future recommendations to improve the technology. In the beginning, in addition to the technologies that Brahim referred to, I will talk about the sodium nickel chloride. It is a technology that is not used very much. It has good energy density and operates well in cold weather, and its life cycle can last a few thousand. However, it needs a lot of high requirements of heating, and the power density is very low. And because of the high requirements of heating, the heat cost of using such technologies is going to be so high. There is also the zinc air cell. It is another technology that is not widely used. It has a high energy density, but it has a very low lifespan. Also, we need in the beginning to charge it like 100 times before it can be used. So it is not evolved for wide use in plug-in hybrid electric vehicle. Now I will address the decision making when choosing a battery. So after the studies conducted, lithium-ion batteries are the most efficient in performance. They can deliver the higher power and energy density. The nickel-metal hybrid batteries also have a good level of performance. It's not as good as the lithium-ion batteries, but it's also good. The lead-acid technology is the cheapest and the most affordable technology, but in terms of power and energy density, it provides a low amount of these specifics compared to the other two technologies. So usually for high performances, one would pick lithium-ion or nickel-metal hybrid technology, and sometimes people would even pick a combination of the cells of these two technologies in one battery. And if you want to have like a low cost, you would pick the lead-acid technology. Okay. Moreover, I will talk about requirements that one should look at when choosing a battery. First of all, there's the load of the car or of the vehicle. So each vehicle has a load, and the battery that can the highest efficiency is the battery that should be selected. In addition, there's also the power and the energy densities, which are the reason behind that the battery is able to supply the load by the vehicle. So the higher the power and the energy density, the better it is to select the technology. There's also the efficiency of the technology. So we have two types of efficiencies. First of all, we have the Coulombic efficiency, which is the ratio of charges entering the battery while charging it to the ratio of charges exiting the battery while discharging it. And we also have voltage efficiency, which is the ratio of voltage needed to charge the battery over the ratio of voltage needed when discharging the battery. We also have finally the cost. Basically, the cost plays an important role in choosing the technology. So if someone is looking for performance and not for cost, he would pick a high expensive performing battery. But if someone has like a limited budget, also look for the cost of the battery. Okay, so as Brahim said, the most used technology is the lithium-ion technology. It has the highest energy and power density, and despite its expensive cost, it's still cheaper than the nickel hybrid metal technology, and it also provides power at a higher stability rate. Moreover, inside this battery technology, we have different chemistries of the lithium-ion battery. First of all, we will a study a comparison between three types of lithium-ion chemistries: the nickel cobalt, the iron phosphate, and the lithium titanate oxide. So the highest energy density was found to be the nickel cobalt chemistry. It can supply up to 170 watt-hour per kilogram of power density. The iron phosphate also has a high energy density, but not as high as the nickel cobalt. And in terms of power potential, all the batteries can supply a good power potential at a high efficiency that can reach 90%. But the nickel cobalt and the lithium titanate oxide to their life cycle by a big percentage, while the iron phosphate only reduces its life cycle by a small percentage. And finally, the lithium titanate is the less costly chemistry. So also, if you are looking for a limited budget, we could pick it. But it has the lowest energy density, which could reach a maximum of 70 watt-hour per kilogram. Now I will talk about the daily use of PHEVs in the life of the consumer. So here, this graph comes from a study of the users of a plug-in hybrid electric vehicle in Norway. Here, the graph shows the all-electric range traveled. So basically, we are seeing how much of the overall of the drivers are being traveled by only using the battery. So on average, in the summer, 60% of the total distance traveled comes from only the battery, and in the winter, it's slightly lower, but it's still high. It's of 53%. This is predictable because in the winter, the conditions are colder and the battery will lose its efficiency. But nonetheless, in both summer and winter, we have a high percentage of the total distance traveled being made only on the battery electric power. We also noticed that there's a high share of electric power by going to work or school, which are the most frequent destinations. So as we see in the graph, in the summer, 66% of the plug-in hybrid electric vehicle users travel more than 70% of their total traveling distance by using only the electric part of the plug-in hybrid electric vehicle. Okay. So now we will talk from the point we talked above about the environmental benefit. So clearly, we have a lot of electric mileage, so we are saving a lot of fuel and gasoline. Fuel and gasoline, of course, have a much higher greenhouse gas emissions than electric sources. So here, another study was conducted in the USA that shows the greenhouse gas emissions for a conventional vehicle, a hybrid electrical vehicle, and 3 plug-in hybrid electric vehicle. We can clearly see that the plug-in hybrid electric vehicle emit much less than the conventional vehicle, and the reduction in some cases can reach up to 41%. Between the hybrid electric and the plug-in hybrid electric, there is no big difference, but the plug-in hybrid electric vehicle still emits slightly less than the hybrid electric vehicle. Okay. in the graph before, we saw different like PHEV10, PHEV30. The number in the name refers to the utility factor that plays a very important role in fuel saving. The utility factor is the amount of electric mileage that the car could go before being charged again. So basically, a PHEV10 can do 10 miles using only electrical power between two charges. So of course, the higher the utility factor, which means we have a higher electric distance traveled, which means that we are saving more fuel and gasoline. So from the study showed above, they also study to show how much fuel is saved. For example, in the US, the PHEV10 saves 20% of gasoline being used in a conventional vehicle. However, for a PHEV with a utility of 40, we are saving even more, which is 55%. So from here, we see the importance of distance traveled electrically. We see its importance in the role that it plays in saving fuel. Now we will talk about an energy recovery mechanism inside the plug-in hybrid technologies. It is the regenerative braking. So it's an energy recovery mechanism that converts kinetic energy and stores it inside the battery. This kinetic energy comes from the fact that when we are braking, the rotors of the motor are turning in an opposite direction than the tires. So from this mechanism, we have kinetic energy that the system will store in the battery, and this energy can be used later. So the battery, in addition to being charged like in stations, can also be charged by braking. Here we have a diagram that shows that when you are accelerating, the battery supplies energy to the axle of the wheels. However, when you are braking, because of the different direction of the motor rotation, the motor will act as an energy supplier to the battery. Before, in the conventional vehicles, while braking, all this energy was dissipated in the heat and it was lost. But now, with this technology, a portion of it is being saved and restored. In addition, it was shown that that a non-aggressive braking can recover more than when we have aggressive braking. So non-aggressive braking softly at a longer distance, and aggressive braking means braking at the highest distance, and the braking is usually very strong and very sudden. So Toyota conducted a test on its 2013 Prius plug-in model, where they tried aggressive and non-aggressive braking. Clearly, as we can see, non-aggressive braking has recovered almost half of the kinetic energy, while aggressive braking only recovered 7%. But nonetheless, both technologies can recover some energy and can charge the battery. It's lagging, but 1 minute. Okay. And now, after talking the fuel saving and reduction in the greenhouse gas emissions, we are going to talk about the cost analysis of the plug-in hybrid electric vehicle. So this graph shows a comparison of 5 vehicles. Some of them are plug-in hybrid. One of them is hybrid electric, and one of them is a conventional vehicle. In the beginning, when we purchased the vehicle, the PHEV have a much higher purchase cost than the conventional vehicle and the hybrid electric vehicle. As we can see, the conventional vehicle costs around $23,000, while a PHEV 40 could cost up to $35,000. The graph continues to show over the years with the operating cost and the fuel cost, how much one is going to be more expensive than the other. We noticed that in 7 years, the plug-in hybrid electric vehicle starts to have a cumulative cost that is less than the conventional vehicles. But this is still considered like a long period, because 7 years on the same car is a long period. And for the hybrid electric vehicles, it will take to 15 years, so that the plug-in hybrid electric vehicle can have a cumulative cost that is smaller than the hybrid electric vehicle. So we need the real solutions to find a way to have cheaper and to encourage people to buy plug-in hybrid electric vehicle for better environmental benefits. Now, after analyzing the state of the technology and showing that we need to reduce the cost, and even though we have a reduction in greenhouse gas emissions, we still need to make further reductions, because as we saw with the hybrid electric vehicle, the reduction was not very high. So first of all, one of the future recommendations is to use different types of energy sources that are being used today. From this graph, we can see the average greenhouse gas emission of a conventional vehicle, a hybrid vehicle, and a plug-in hybrid vehicle that is using different sources of energy. So clearly, as we said before, the conventional vehicle emits like 30% more than any plug-in hybrid electric vehicle. However, compared to the hybrid electric vehicle, for example, if we use we have like 10% more greenhouse gas emitted than the hybrid electric vehicle. Moreover, some technologies that are not exactly fully developed today, like renewable sources, gas, and nuclear energy, they are not developed in the production of plug-in batteries. We can see that they have much more greenhouse gas emission being reduced than other technologies. So for example, using nuclear energy, we can have a maximum of 150 grams of equivalent CO2 gases per mile, while using old coal, the 2010 technology, it can emit up to 325. So the nuclear, biomass, and the renewable sources are the most efficient, and in the future, we should switch to only use these technologies. We also have two types of plug-in hybrid battery technologies that are being developed, but they also need a little bit more studying and work before they are deployed in practical applications. So first of all, we have the lithium-air battery. It can reach a power density of 11,000 watt-hour per kilogram, which is much bigger than the current technology's power density. However, it is only present in labs, and it's not used in practical applications, and scientists have not been able to translate the theoretical value into a practical value in real life. This is the same condition for the lithium sulfur battery. It has a potential of 3,350 watt-hour per kilogram theoretically, but practically it only reaches 10% of this value. It also has a low conductivity that could be a problem while the vehicle is operating. And finally, its life cycle is really short, as it can only be charged up to 50 times. Okay. Now we will give a recommendation in the cost efficiency, particularly of the fuel and the operating cost. So here we have a study in Germany of two cars bought in 2014, and they were used over 4 years for a total distance of 14,000 kilometers. So we have a conventional ICE and a plug-in hybrid electric vehicle 70. As we can see, the purchase cost of the plug-in hybrid electric vehicle is much higher than the conventional ICE. It's almost 9,000. But the resale value of the plug-in hybrid electric vehicle is higher. And the fuel cost of the plug-in hybrid electric vehicle is around $6,000 less. This makes sense because we only used a specific amount of fuel, in the plug-in hybrid electric vehicle, while in the conventional ICE, we use a very big amount because the car is running entirely on fuel. However, in the plug-in hybrid electric vehicle, we have an electricity, but in Europe, electricity cost is much less than the fuel cost. And as we can see, all other operating conditions are of less value in the plug-in hybrid electric vehicle than in the conventional ICE vehicle. So in the end, we almost have equal values between the conventional ICE and the plug-in hybrid electric vehicle after just 4 years of use. So in Europe specifically, we have a high fuel cost. So one of the future recommendation can be adopting a similar pricing like the European Union, where the cost of fuel is high and the cost of electricity is slightly lower, to encourage people to shift to plug-in hybrid electric vehicles. Okay. Another recommendation is making heavy technological advancement. So basically, here we have a table that compares the energy density and the energy cost of plug-in hybrid electric vehicle now and in the future, depending on if the technological advancement and progress will be low or high. So any level of progress will reduce cost and increase efficiency. But if the progress is high technologically, we will have significant increase in efficiency and a significant cost reduction. For example, the energy cost of a plug-in hybrid electric vehicle with a utility factor of 20 was $100 kilowatt hour in 2015. With a high technological advancement, it can reach only $160 per kilowatt per hour, while for a low technological advancement, it will reach 210. So we have a reduction in both cases, but with high technological advancement, there is a much bigger reduction, which can also encourage people to adopt plug-in hybrid electric vehicle, which will ultimately have a better impact on the environment. Okay, another type of technological advancement, not only in the energy part of the technology, but also in the manufacturing of the batteries. So the manufacturing of the batteries play an important role in the total cost of the vehicle. So even if you have a low technological progress, we will have lower manufacturing costs in the future. But here the diagram shows the difference between the high technological progress and the low technological progress. So as we can see, for example, between 2020 and 2030, in both cases, the cost will decrease. However, with high technological progress, the cost will even decrease more by $3,000 to $4,000, which could make people more attracted to buying plug-in hybrid electric vehicles. So it is critical to heavily invest in technological progress for the plug-in batteries in order to reach the possible potential of these batteries.